Okay, so we have this 1Le0 beta hairpin peptide, and it has 4 tryptophan amino acids that are responsible for its folding into a beta hairpin. And just to demonstrate um, where these tryptophan are, I'm going to open the PDB file, and we can see that the first amino acid is a serine, and then the second amino acid is a tryptophan. So residue 2 is a tryptophan. If we keep scrolling through, we see that residue 4 is also a tryptophan. And then we continue scrolling through, and residue 9 is a tryptophan, and residue 11 is a tryptophan. And there are a total of 12 amino acids. The last N-terminal amino acid is lysine. So in this representation, I've shown those 4 tryptophan and I've colored them in spectral order. So residue 2 here in red is a tryptophan that interacts with residue 11 tryptophan, which is in blue. Residue 4, interacts with residue 9. So the yellow is residue 4 and the green is residue 9. And you can see how those tryptophan align their hydrophobic rings sort of perpendicularly to one another to pull the beta hairpin together. And so what we want to do is look at how the structure is affected by mutating these one or more of these amino acids. I'm going to only demonstrate mutating one, and for hypothetically the largest effect, what I'm going to do is mutate either residue 2 or residue 11 because those are closer to the ends, and what I would expect then is that these two ends will separate from the lack of tryptophan interaction. And what we could do is replace those hydrophobic amino acids with something that is polar. And so we have a choice here of polar uncharged side chains: serine, threonine, asparagine, and glutamine. Presumably, if we were to replace a tryptophan with a serine, we might also have some steric effects that are involved. And so what I'd like to do is to avoid as much as possible any steric effects, I'm going to use a large side chain. I'm going to use glutamine for the mutation. And what I'll do is I will mutate residue 2 in this demonstration. So I'm going to open the mutator, which is in the modeling menu of the extensions menu. There's a mutate residue, and I already have my files open, but I'm going to just browse and make sure that I'm getting the right ones. So I will load the PSF file, and I will load the PDB file and just check that those look correct. And then I'm going my output file. I'm going to call 1le0 underscore. I'm going to mutate tryptophan 2 to a glutamine, and so the ID of the target is 2, and the mutation is going to be glutamine. And I'm going to run the mutator. I'll see in the TK console that there's some output, and then I can see here that it has loaded my mutation. And just to check it, I'm going to create a representation. It still has that beta hairpin structure. And so what I'm going to check is that the residue name, is glutamine at residue 2. And sure enough, residue 2 is now glutamine. I can just check all the tryptophans as well. So if I were, for example, to try and do res name glutamine and res ID 4, it's not going to work. I need to make this a tryptophan, and it shows up. We'll check residue 9. And residue 11. Okay, so now we have this mutated protein or peptide, and we can simulate this as well as what I'll call the wild type. This is a de novo protein that was created for the study of beta hairpin, so it, as far as we know, doesn't exist in nature with this particular amino acid sequence. But I'll call for now the wild type has the 4-tryptophan, and the mutated has now a glutamine at residue 2. And so we'll simulate these in vacuo, so in vacuum, no solvent. But in the next video, I'll show you how to solvate these so that we can also simulate them in water.